Welcome back to the laboratory demonstration. The next instrument I have picked here is dial gauge. Dial gauge is an instrument that is used in which the principle is used that the reciprocating motion is converted into the circular motion, and that gives us some reading. I will show you the principle. First let us see the dial gauge, the components of this dial gauge. This is the dial gauge and its make is Baker. So, this dial gauge has various components. The first component is bezel. The bezel is the outer part which can be rotated to adjust this 0. So, this bezel can be used to adjust the 0. We see we can move it if there is an arrow, if there is a 0 error, we can adjust it. Here we have the positive error, so we can adjust this. So, also we have the markers. We can see in the black colors there are two markers. These two markers are used to mark the reference point, and for the start of the measurements, these markers are generally kept at the reference point, or maybe one of the markers could be kept at the 0 as well if required. Also we have two pointers inside. One is the main pointer, one is the small pointer. You can see we have the main point at the lower end, which is at the plunger with the main point. If we put it up, if we push it up, the reciprocating motion, if we push it up slowly, you can see the larger needle is moving very quickly. We can see the specifications here that it is written at 0.01 to 10 mm. Now 0.01 is if I move my plunger a little above, you can see a little movement. Yeah, it has moved 3 readings forward. Okay, that means it has moved 0.01 into 3, 0.03 mm forward, the bigger needle I am talking about. So, when I push it a little more, it makes one complete rotation from 0 to 0. You can see the larger needle is moving in the clockwise direction, and the smaller needle is simultaneously moving in the anti-clockwise direction. We will do it again. It is moving in the clockwise direction. The smaller needle is moving in the anti-clockwise direction. I will explain the principle. You can see the larger needle has made one full rotation. That means it has moved 0.01 into 100. You can see that there are total 100 divisions on the larger scale, which it has covered in one rotation, and the smaller circle, the smaller needle you can see which has moved anti-clockwise, it has just moved one division ahead, one division forward. So, that means 0.01 to 10 mm is the range. The minimum division, the minimum reading that it can give is 0.01 and the maximum is 10 mm. If I push the plunger completely above, you can see it has though it has gone more than 10 mm here, but the sensitivity of the instrument or the range of the instrument is that can be read is 10 mm. So, we have plunger here, above the plunger we have stem in which the plunger is moving. So, we can see the reciprocating motion of the plunger is giving the circular motion to the needle. The principle behind this is the gear train only. If I push the plunger above and leave it, what happens? The needle comes back to the original position. That means that there is some spring mechanism that is working in. So, it is an helical spring here. So, how it is working? I like to explain it in this way. This is actually my plunger, and it is actually a rack and pinion. I have a pinion here. When it moves up and up or down, this pinion rotates. This pinion rotates. Well, let me say it is moving in upward direction. This pinion will rotate. If it move in upward direction, this is rotating this direction. And this pinion is attached to another gear here, which is this one. And I have my pointer P1 here. Now, if you see, if I move it in the upward direction, you can see the dial gauge. If I move it in the upward direction slowly, the pointer, the main pointer is rotating in the clockwise direction. You can see it here. If I move it in the upward direction, this gear, I will call it gear 1. This gear 1 is rotating in anti-clockwise direction. I will put it anti-clockwise. Gear 2, which is rotating in clockwise direction. So what happens with the small movement of this plunger? There is a large movement, because you know this is a small pinion and the gear ratio is there based on which the calibration is done, which is based on the gear 1 is the small movement of gear 1 is giving a big movement to the gear 2. So here rack and pinion, this is rack and pinion. So this is the pointer P1. So this small pinion or the I would say the gear 2 is also connected to another gear, which is my gear 3. This small gear, gear 2 is rotating gear 3. This is my gear 3, and also I have a pin here, pointer here. So this is my pointer P1 and this is my pointer P2. You can see with the rotation of the dial gauge, with reciprocating movement of the dial gauge, the pointer 1 is making one full rotation and the pointer 2 is rotating in the other direction. You can see if this is rotating in anti-clockwise direction G1, G2 is rotating in clockwise direction, and G3 would obviously rotate in the anti-clockwise. And also the velocity ratio or the gear ratio is such that one full rotation is only making one division in the smaller pointer. One full rotation of the bigger pointer is making one division in the smaller pointer. So it is calibrated in this way. Also you can see that when we leave the dial, we leave the plunger or the pointer, it comes to the original position by itself. So this spring mechanism is attached here. There is a spring, that is the helical spring. This helical spring stores energy when the plunger is pushed up, and when it is left, because the energy is stored, it releases the energy and the plunger comes back to the original position. Better I would say the point of contact comes back to the original position. This is the principle of the dial gauge. What is the application of the dial gauge? In case of rotating shafts, the dial gauge is put on the rotating shaft so as to see whether there is an offset or play or eccentricity. This can tell us whether what the eccentricity is. Whatever the movement is, we take the mid value. You can see the dial gauge is attached to the stand here, the dial gauge holder. In the dial gauge stand, we can say that we have a kind of a universal connection in which dial gauge can have any kind of, it can move in any direction. It has actually the 6 degrees of freedom. It can, you see, it can move in this direction, it can move in this direction, it can also move in this direction. Yes, okay, this is one more degree of freedom, that is height can also be adjusted here. So it can be fixed wherever it is required. So this is the use of dial gauge. Yes, with dial gauge, I can also now talk about the dial vernier. So this is a vernier caliper. Actually, there is no principle or the movement like dial gauge, but it has a dial. It has a rotary scale. It is a circular scale here, you can see. It has also the main scale reading, which are calibrated in inches and mm. It has this vernier scale. The use of this scale is that we can adjust this 0 at point whenever we like. So you see, wherever we need, at this point also we can adjust it this 0, at least of the vernier scale. You can see here that its least count is 0.001 inches. So this is another vernier caliper which is having this circular scale, and it can be adjusted. This is the advantage. However, the other uses are same. It has internal jaws, external jaws, it has this depth gauge and the screws, the fine adjustment screw. Let us meet in the next part of the lab demonstration. In this demonstration, I will discuss about a micrometer. This is the laboratory demonstration for the course Engineering Metrology. In this course, we are discussing about the measurements, about the various instruments for linear measurements, angular measurements. These two major equipments for linear and angular measurements I am discussing in this module. So, micrometer that we have selected here is a Mitutojo micrometer. This micrometer is having range from 0 to 25 mm and the least count is 0.01 mm. So, you can see the specifications are given here. I will just discuss the components of the micrometer. We can see that the maximum measurement that can be taken here is 25 mm and the least count is 0.01 mm. It is important to note here that the least count is half the least count of the Vernier caliper. The least count of Vernier caliper was 0.02 mm. So, this is 0.01 mm. That is the readings that we had in Vernier calipers were like 44.4, 48, 12.28. Here we also can have 12.27 or 12.29. So, it is more sensitive. Also, the micrometer can or is used to measure the external dias only. It is not very much possible to measure the internal diameter, internal lengths using the micrometer. So, the various components of micrometer you can see here are, the first component is the anvil. The anvil is the portion that is the fixed jaw. If I open it a little, when I rotate it, you can see it is opening. You can see it is also known as screw gauge. Screw gauge, why it is known as screw gauge? Because it is working on the principle of the nut and screw. It is just like loosening or tightening a screw. Okay. So, when we are loosening the screw, this component is anvil, that fixed component is anvil and it is calibrated based upon the surface. This surface is very flat, the anvil surface is flat, the flatness is quite precise. So, we have a thimble or spindle here which can be using the screw which can move forward or backward, and we have the lock nut. At any point we can lock the reading using this lock nut. So, this lock nut is used again for the convenience once we take the reading, and then we can lock the reading at this point and then note down it very easily, conveniently. So, we have two scales here, the main scale, this is the main scale you can see, and the micro scale, the circular scale we call it. We can see on the main scale between 0 and 5, there are 10 divisions. It looks like that there are 5 divisions. However, on the upper side there are 5 divisions and there is a division at the lower side as well, which are in between the divisions of the upper side. So, you can see the first division on the upper side, that is 1 mm, first division on the upper side is 1 mm. If we see at the lower side, this division is between 0 and 1, that is 0.5 mm. So, if I close it completely, you can see that when I close it completely, at the end you will listen to a click noise. See there, click. Again I open, again I close, click. This click is actually the ratchet mechanism. It can move in one direction only. When I open it, there is no click or there is no play, but it can, yes, when I rotate it clockwise further, it will keep on giving the click noises clockwise further, it will keep on giving the voices like click, but one click is enough to let us know that the pressure is enough, that the workpiece or our movable, that is our movable spindle has touched the workpiece. So, that is enough, one click. This is a ratchet attachment. Other components here are, we have adjusting net and the frame, the lower frame is known as U frame or U-shaped steel frame. Then we have thimble here, then we have sleeve here, we have spindle. I have already discussed, the movable part is known as spindle. So, these are the major components of the micrometer. The principle on which this micrometer work is the principle of screw. It is the principle of the screw gauge, that is the screw pitch. I can write the principle of micrometer. So, micrometer is based upon a principle of a screw to amplify the small distances that are too small to measure directly into large rotations. You can see if I make one full rotation, 0 is again coincided with this center line, it has moved 0.5 mm forward. We can see the line, there is center line, there is center line here. The line below the center line is 0.5 mm. That means one rotation on the circular scale we have actually 50 divisions. You can see from 0, 5, I will rotate it to show it 0, 5, 10, 15, 20, so on. I have 50 divisions and one rotation will take it forward to 0.5 mm. So, this large rotation of screw only brings small movement in our spindle. So, this is the principle, one full rotation only 0.5 mm, another full rotation only 0.5 mm. So, this is the principle on which is based upon. Also, the least count of the micrometer can be calculated very easily. You can see that the 0.5 mm was seen 0.5 mm in 50 divisions. So, that means roughly we can say the least count would be 0.5 by 50 is equal to 0.01 mm. However, the general relationship here is the least count is equal to pitch by number of divisions on circular scale. So, pitch is in one rotation, it is the pitch of the thread, like we have discussed the thread terminology 3D of that. One rotation, how much forward or how much ahead our screw goes in one rotation. In one rotation, that is pitch divided by number of divisions is the least count. It is a simple relation here. So, this is our least count, and the measurement value or the measured value, the measured value is equal to main scale reading plus least count into circular scale reading, and if it is main scale reading, and if there is some error, if in the beginning the 0 is not coinciding with the center of the line, that error has to be adjusted, this minus or plus minus error. Okay. Actually, if I put here 0 error as we have discussed, it is always subtracted. So, this minus 0 error, there are 3 terms. So, let us try to find a few dimensions using micrometer. So, let us first pick a simple wire, steel wire. So, the procedure is we will again loosen it to a length, to a gap little more than the feature or the dimensions that to be seen, that is to be measured. Then we will add the wire, then I will put the wire on the anvil and close it so that the ratchet makes one click noise, one click sound. Yes, now I lock the nut. Now I can take this out. So, you can see on the main scale the reading is more than 3.5, it is 3.5, you can see reading is more than 3.5, however it looks like it has crossed 4, but if I see the center line is coinciding with the 49th division, one division before 0. So, I am putting 3.5 plus 0.01 into 49. So, is there any 0 error? Let me close it to see, is there any 0 error? So, can you see that the 0 is exactly coinciding with our center line or not? Yes, it is. It is coinciding. So, there is no 0 error. So, this error is 0. So, this reading, this diameter of the wire is 3.5 plus 0.49 is equal to 3.99. Wow! This wire, when it was purchased, it is purchased in the dimension 4 mm. So, we can see the reading that we are getting at some point is 3.99. So, the sensitivity, you can say, if the wire is purchased 4 mm is the wire and plus minus 0.02 is the tolerance. So, this is acceptable. So, 3.99 mm is the dimension. Also, we can see the reading at another point. It might be I think maybe 3.98, 3.97 maybe, because 0.01 mm is not it cannot be identified by naked eye or cannot be just felt by hand as well. So, this can be done. And okay, I will do one experiment. The diameters that we calculated using Vernier caliper, I will try to see those readings, diameter of the dimensions of the component that we used, that we measured using Vernier caliper. I will try to see those values, one or two of those values using the micrometer as well. So, let us try. So, because the values that we had there were in 0.02 places, okay, the even places of decimal and the second place were there. Now, let us see the single place, the odd places will also be there. So, the sensitivity is 50% of that. So, the sensitivity is double of that and the reading would be 50% of that, half of that. So, we have decided to conduct an experiment to measure the length of the pencil at various places. So, actually this is the pencil, let us see, not length, sorry, the thickness of the pencil. What is the general thickness of the pencil here? If I do it using this, so with one click and locking the nut, this length comes, this thickness comes to close to actually you can see that this reading 0, first reading is coinciding, this first reading is coinciding after this 5th, 6th, 7th, 7.01. So, we can see the length of the thickness of the pencil at one point is 7.01. Now, let me unlock it and take the second reading at about point that is a little deeper than the starting point. Ratchet gives the click, I lock, the reading here is, you can see the reading here is now a little lesser, 44th reading is coinciding here. If you see, the 44th reading of the circular scale is coinciding with the main scale and it is after 6.5. So, 44 plus 0.44 plus 6.5, 69.4. So, we have got two readings here. So, for the pencil thickness, it is 7.01, 6.94. Let me take another reading on the same surface here with one click, locking the nut, taking this out. In this we have 20s, it is actually 5, 6, 7, 7.5 and 25. Yes, this is a little weird. So, it is 7.75. You know, the pencil is an instrument, is a tool that is just used, is to be used in the hand, and the general dimension of the pen or the pencil that we use is between 5 mm, between 6 or 7 mm to 15 mm for the precision writing. Pencil is a kind of a precision writing, and for the whiteboards etc., it might be 20 mm, might be, when the larger it becomes, the lesser is the sensitivity or the precision in writing. So, in general, the thickness of the pencil, if you see, is 7 mm, but if I use it, if I use the micrometer to calculate, you can see this variation 7.01, 6.94, 7.55. So, this is a little weird, because this is just made to hold in the hand. So, the range might be between 6 point, because you know there is a paint also, the paint is also there on the pencil. This is also having some thickness, and it is not very important to design it exactly close to 7 mm. It can vary from 6 point, I can say 6.5 mm to 8 mm to so on. So, this is actually one way to see that how the things are designed. Had it been a key, had it been a metal hexagonal key which has to be inserted in something like maybe go or no go gauge, okay, so it has to be more accurate, but it has just to be held in a hand. We need to design it in a very precise or accurate way. So, this was about the micrometer. Next, I will discuss about the surface plate. So, here we have a surface plate. Surface plate is actually the basic or fundamental, I can say, tool that is kept in a metrology lab, because you know the foundation of all this geometric accuracy and all the dimensional measurements is the flat plane, which is actually provided in the workshops and inspection laboratories by the surface plate only. So, this is a cast iron surface plate. The surface plate can have high accuracy. The accuracy can be 10 micrometer to 0.01 mm per 3000 mm of grade. So, the accuracies can be different. These days actually this is an old surface plate which was kept in IIT Kanpur. I think this was purchased about 40 years back. So, these days surface plates which are available are of the stone, like granite surface plate. The black granite surface plate is also there. So, the sensitivity of the black granite surface plate is 1/10,000th of an inch. So, this is one surface plate. It is having dimensions 15 inches into 15 inches, the length and width, and the thickness is 1 inch. You can see that it is a smooth surface. We can, using the spirit level, we will next move to the spirit level, we can see that whether it is kept properly flat to the base or not. Okay, this is one thing. Surface plate forms the foundation of a metrology lab. The most surface plates are rectangular, which are having 4/3 length ratio, that is the aspect ratio is 4/3. They may be square, maybe they may be round, or they are geometrically most correct for creating a flat plane by 3-plate method. The commonly used cast iron surface plates have special ribbing and structural formations under the surface, so that these will be as light in the weight as possible. You know, it is not very solid surface plate, it is having ribbings below it, you can see. So, as because to reduce the weight, so it is not the whole solid, so to reduce the weight this is there. Also, the true plane of the surface plate is not machined or scrapped until it has really aged and all internal stresses have subsided. Actually, the granite surface plate is a very good adjustment. It is very tremendous replacement of the cast iron surface plates, because granite surface plates can be grounded again and again. Also, the cost is less, the weight is lesser. This surface plate, the surface is hard, there is a surface hardness there. Whenever we need to machine it, the surface is again has to be hardened, and there might be certain bumps etc. Actually, the sensitive hand can see whether there are bumps or not. Okay, this is an old surface plate, you can see there are small wear and tear here, okay, but this is again workable. We will use height gauge, spirit level and other instruments on this surface plate. Okay, the next instrument is filler gauge. Filler gauge is a tool which has many strips in it. So, these are actually different strips in here. The feeler gauge is used to measure the gap bits between two flat surfaces where it is difficult to reach. So, feeler gauge can reach there, and these widths, for instance this is 1 mm, this is 0.05 mm, this is 0.10 mm. The various kinds of feeler gauges you can see. We are also having a feeler gauge which is width packs, width packs is there, and it is having 10 blades in it. You can see the dimensions, it is having 10 blades from 5 by 100 to 80 by 100 mm. So, feeler gauge can be used, for instance there is a spark plug here, the gap between spark plug, if you say the gap between spark plug is 0.6 mm. This 0.6 mm spark, whenever the element deteriorates, when the spark plug gives the sparks continuously, the inner element of the spark plug deteriorates and the gap increases. So, what we see, the mechanic would tap from the top of the spark plug to bring the gap back to the desired value. Desired value is 0.6 mm. So, feeler gauge, however, the skilled the mechanic can just do it by itself, but the proper way is to use the feeler gauge of 0.6 mm. You can see this, if this is a feeler gauge, one of the leaf of the feeler gauge I am trying to put it in, it is not going it properly. So, I am trying to pick one leaf of the feeler gauge here, the largest leaf that is 80 by 100, that is 0.8, 0.8 is not going in, 80 by 100, 0.8 is not going in properly. So, the second leaf which is exactly 60 by 100, it is 0.6, it is going. So, it is telling us that the gap between the upper and the lower electrode in the spark plug is 0.6 mm, and this can be adjusted. So, feeler gauges are of various types. We have go no go gauge, tapered gauge. Go no go feeler gauge, it has a thick base and a thinner tip. It has thick base and a thinner tip. The thinner end of the gauge can go into the gap and the thicker body will not go. So, this is go no go. This is thin, this is thick. Then we have straight leaf feeler gauge, like we have here. This is a straight leaf feeler gauge. The whole the leaf is the thickness of the leaf is uniform throughout its length. Then we have metric feeler gauge or metric and imperial feeler gauges. There are two different feeler gauges combination. Metric feeler gauge is the one which gives measurements in the hundredths of a millimeter, and imperial is the inch type, it gives the measurements in the thousandths of an inch. So, it is a combination of metric and the imperial feeler gauges. Then we have tapered feeler gauge. A tapered leaf feeler gauge has leaves that are thin towards the tip. So, this feeler gauge is actually the tapered one. If you see the leaf here, it is tapered toward its tip. So, the tapered feeler gauge is this one. Then feeler strip is here, it work identically to feeler gauge blades, exception is that they are not connected in a set and either end can be used to measure. So, this is feeler strip, it is same here and here, okay. This is only one strip, same width here. So, these are various kinds of feeler gauge. Oh, also yeah, this is an angle feeler gauge, angle feeler gauge or offset. In this gauge, the blades are bent towards the tip for the easy access to the intricate part of the motor. There are certain parts in which we cannot insert the straight part, we need to have some bend to insert it properly. So, this is the feeler gauge. Feeler gauge can also be used on the surface plate to see if there is a gap, if there is a flatness or not. For instance, when I will use the height gauge, we will try to insert the thinnest of the feeler leaf between the base of the height gauge and the top surface of our surface plate only. So, does it insert, is there a gap or not? So, we can see that. So, sometimes there can be warpage, there can be bumps. So, at some point the feeler gauge would insert, at some point it would not. So, this is the purpose the feeler gauge is used. Just like feeler gauge, the other gauges like pitch gauge or thread gauge, that we will discuss further in the next part of our laboratory demonstration. So, as of now, thank you, and we will meet again to discuss other instruments like pitch gauge, vernier height gauge, then sine bar, combination gauge, combination set actually, slip gauges, and vernier or gear vernier, yeah. So, these instruments will be discussed. Also, we will also go to the laboratory to see the demonstration how to note the coordinates using coordinate measurement machine. So, we will meet in the next session in the laboratory demonstration only. As of now, thank you.